Experiment 13, we will be exploring the conservation of energy. More specifically, we're going to be looking at the conservation of heat energy. In order to do this, we need the heat equation. So the heat equation is Q equal to mc delta T. This translates to the next equation, which has Q equal to mc, and then instead of delta T, we have T final minus T initial. So let's look at what these variables mean. For Q, Q is the symbol for the heat transfer. It is measured in calories in this course. For our M variable, M is mass, and that needs to be measured in grams for this lab. Next, looking at the C variable, that is the specific heat, and we'll get that value from the table. In this particular lab, we'll be looking at water as our substance, and since specific heat is dependent upon the type of substance we're using, we'll use the specific heat of water, which is 1. The delta T in the equation, delta T stands for change in temperature, and we're going to be measuring temperature in degrees Celsius. So let's look at specific heat a little bit more closely. And remember that specific heat was the C value in that equation. So off to the right, there is a table of specific heats, and specific heat changes depending upon the material that we are talking about. So specific heat is the capacity of a given substance to absorb a given amount of heat. So the higher the specific heat of a substance, the more heat energy it takes to raise that substance 1 degree. So looking at this table, you'll notice that water has the highest specific heat. What that means is water's ability to absorb heat is much greater than the other substances before it would raise a degree in Celsius. Water is what we're going to be looking at in this lab. So the specific heat we'll be using in this equation will be that value of 1. So what is the conservation of heat energy? It's when you have two materials at different temperatures and there's a heat transfer involved. As long as this is done in an insulated environment, the heat energy lost will equal the heat energy gained. So what we're going to be looking at is warm water versus cold water. And what we're going to do is we're going to mix the warm and cold water together. We're going to see a heat transfer from the warm water to the cold, because we always have heat transfer from the hotter object to the colder object. We're then going to calculate our Q values, our heat values, and we'll see that however much heat energy the warm one lost, that's going to be the same as the heat energy gained by the colder one. So for the lab procedure, we are just going to be doing part 1 of this lab. We will take hot water and cold water. We're going to take the temperature of each. And when we do this, we do it in a styrofoam cup with a lid to try to keep it insulated. That way we're not losing heat energy to our surroundings, and that way the cold water isn't gaining heat energy from the surroundings because it's insulated. We're then going to take this hot water and cold water. After we take the temperature, we're going to mix them together. We want to make sure to take the temperature of the hot water and the cold water immediately before mixing them. Because if we take the temp of the hot and cold water and then walk around the lab doing something else, what's happening is that we might be losing some of that heat energy, and the temperature is going to change of the hot water and the cold water. So we want to take the temperatures right before mixing for the most accurate results. So we take the temp of each and then mix them together, stir them so that the heat transfer, until the heat transfer is complete, and then we take the temperature of the mixture together. So here's some mass data for trial 1. So before we take the temperatures of the hot and cold water, we first need to get the masses of the calorimeters. So when I use the term calorimeter, what I'm referring to is that styrofoam cup with a lid. A calorimeter is just meant to insulate the water in the cup to make sure no heat energy is lost or gained, or at least very little lost or gained during the experiment. So when I say mass of first dry calorimeter, 4.5 grams, that is the mass of our first styrofoam cup. We then add some cool water to that styrofoam cup and mass it again. So the mass of the calorimeter and the cool water at 102.4 grams is the cup with the water in it. To figure out the mass of just the water, this is a calculation that you'll need to do, subtracting the previous two values. So you're going to take the mass of the calorimeter with the cool water, 102.4, and subtract the 4.5 from that. Because what that does is you're subtracting out the cup or the calorimeter, leaving you with just the mass of the water. And notice after mass of cool water, I added this variable m sub c. M for mass, and then the sub c for the cold or the cool water. Next, we need a second cup to put hot water in. So the mass of the second dry calorimeter or cup is 4.5 grams, the same as the first cup. We then add some warm water to it, getting a total mass of 85 grams. Once again, we need the mass of just the warm water by itself. So by subtracting those two values, we subtract out the cup itself, and we're left with just the warm water. Now the variable that I'm using for the mass of just the warm water, I actually used m sub h for hot instead of warm water. These are the mass values that we're going to be plugging in to the heat equation that we saw on the first slide. Next, we need to get our temperature data. So you'll notice there are two trials in this lab. So this is just the mass data and temperature data for trial 1. So we get the hot water and the cold water. We have massed them, so now we take the temperature right before mixing them. Once we have the temperature of the mass of the hot water and the cold water, we mix them and then get a final temperature. Those values are shown below. So our initial temperature for our hot water is 82 degrees Celsius. Our initial temperature for our cold water was 23 degrees Celsius. Once we mix them and the heat transfer was complete, we get a final temperature of 50 degrees Celsius. Next, we need to do some temperature calculations. So you'll notice in your lab manual, in the table, it asks you to calculate for data item number 10, the change in temperature of the cool sample and also the change in temperature of the warm sample. So what it's asking for is that delta T, because remember, delta T means change in temperature. So in order to do that calculation, you're going to take the final temperature that we have, the 50 degrees Celsius, and subtract the initial temperature. Notice though, we have two initial temperatures. So that means you're going to be doing this calculation twice. Once for the hot water sample and once for the cold water sample. Your final temperature will be the same for both calculations. It's the initial temperature that's going to be different for each. So to calculate the change in temp for the hot, you're going to take that 50 degrees, the final temperature, and subtract out the initial temperature of the hot water, 82. Notice when you're calculating the change in temperature of the hot, since the hot water lost heat, you're going to have a negative delta T. When you do the change in temperature of the cold water, you're starting with that final temp of 50 degrees and subtracting out the initial temp of the cold water, which will be 23. Since the cold water gained heat energy, it went from 23 degrees up to 50, you're going to have a positive change in temperature. So this is how it's going to look on your data table. So when you go on your data table, Data item number 7 says temperature of cool water. That's where you're going to be putting the 23 degrees Celsius. The next item, number 8, is the temperature of the warm water, where you would fill in the 82. And then data item 9 is the final temp once they're mixed and the heat transfer is complete, getting a total of 50 degrees Celsius. For data item 10 and 11, you do those calculations that we discussed on the previous slide, noting that your change in temp of your cool sample will be positive, and the change in temperature of your warm sample will be negative since it lost heat energy. Next, we have to calculate the heat energy lost. So since we're calculating heat energy, we need that equation Q is equal to mc delta T. So for trial 1, the heat energy lost, we're going to be using the data from the hot water or the warm water sample, because it's the warm water that's losing heat energy to the cool water. So to calculate the heat energy lost, we're going to take the mass of the warm water, that M sub H, data item 6 in your table, multiply it by C, remembering that C is the specific heat, and then multiplying it by the change in temperature. The C value, since it's water, is 1 calorie per gram degrees Celsius, just like we saw in that table of specific heats. To figure out the delta T, you're using the change in temperature of the warm sample that we calculated. That is data item number 11 on your table. Multiply those 3 together, and remember, the units on heat energy are calories. Show your work and also put your units. For the second calculation, we're calculating the heat energy gained. So we're using the same equation, but different data. For the heat energy gained, we're using the data of the cold water sample because the cold water gained heat energy. It got warmer. M sub C is the mass of the cool water, data item 3 on your table. Since we're still talking about the same type of substance, we're still talking about water, the specific heat value of 1 stays the same for both the cool and warm water samples. Your change in temperature of the cool sample is data item 10 on your table, and this should be a positive value. Show your work and don't forget your units of calories. The third calculation is asking us what is the absolute sum of the energy gained and lost in the 2 trials. Then it gives you an equation, and this equation has bars around it, and what those bars are absolute value. So when you do this calculation, when you do this addition, it means that you're going to get a positive number. So even if it comes out negative, you need to change that to a positive. To calculate this, you're going to take the heat energy gained that you calculated in the number 2 calculation and add it to the heat energy lost. Your heat energy lost is going to be a negative value, and the heat energy gained is going to be a positive value. So due to the conservation of energy, theoretically, the answer to this question should be 0. So the heat lost and the heat gained should equal 0, because when 2 materials at different temperatures are involved in a heat transfer, the heat energy lost should equal the heat energy gained. Now, when you do this calculation, it's not going to be exactly 0, because even though we had the styrofoam cups trying to insulate our hot and cold water from the surroundings, it wasn't foolproof. Some heat energy was lost, some heat energy was gained, so it's not a perfect environment, a perfect situation. So you will get a value here, but the value won't be extremely large compared to the numbers you're adding. So it should be under a few hundred calories. So next, I'm giving you data for trial 2. So it's the same type of experiment. We are taking cool water and warm water, the temperatures of both, mixing them together, and doing the same calculations that you saw on the previous slides. So I'm using the same styrofoam cups, so you'll notice the calorimeter 1 and the second calorimeter, when they are clean, empty, and dry, are 4.5 grams, just like they were in trial 1. The mass of the first calorimeter and the cool water is 119.5 grams. You need to calculate the mass of the cool water by subtracting those two values. The mass of the second calorimeter with the warm water is 54.5 grams. You need to calculate the mass of the warm water by subtracting out the styrofoam cup. Next, here's your temperature data. So now we have temperature of the cool water being 15 degrees Celsius, so a little bit colder than in the last example. The temperature of the warm water, also 95 degrees Celsius, a little warmer than in trial 1. Once those two were mixed together and the heat transfer was complete, we get a final temperature of 39 degrees Celsius. So for data item 10 and 11, you need to calculate the change in temperatures of the cool sample and the warm sample. So the change in temperature of the cool sample, you're going to be taking the final temperature of 39 and subtracting out the initial temperature of the cool water, which is 15. So you should get a positive number there. For delta T hot, change in temperature of the hot, you need to take the final of 39, subtracting out the temperature of the warm water initially, which was 95, getting a negative value there. You then use your data to do the 3 calculations that we did for trial 1, this time doing them for trial 2. So you start with your calculation of the heat energy lost using the mass of your hot water and the change in temperature of your hot water from your data table. You're then calculating the heat energy gained. This time, since the heat energy is gained by the cold water, you're using the data for your mass of your cold water and the change in temperature of your cold water. Last but not least, the absolute sum of the energy gained and lost. So whatever you calculated for those first 2 calculations, add those 2 values together. One of them is going to be positive, the other is going to be negative, and report your answer in calories. So we are skipping part 2. So if you turn to page 64, you'll say there's part 2, data and results. You do not need to do that part. I do want you to answer question 4, the last question on page 63. When you turn the page to page 64, you can cross out that table. You are also not doing any questions on page 64. So questions 8, 9, 10, and 11 all pertain to part 2, so you will not answer those. Neither will you answer number 12. The only question I want you to do remaining is number 13, where it asks, why was the water massed before the temperature was measured? Numbers 14 and 15 are dealing with part 2, so you will not answer those as well.